So we have sequences, mathematical induction, and recursion still. This section is strong mathematical induction and the well-ordering principle for the integers. Strong mathematical induction is similar to ordinary mathematical induction in that it is a technique for establishing the truth of a sequence of statements about integers. Also, a proof by strong mathematical induction consists of a basis step and an inductive step. However, the basis step may contain proofs for several initial values. And in the inductive step, the truth of the predicate P of n is assumed not just for one value of n, but for all values through k. And then the truth of P of k plus 1 is proved. Okay? The principle of strong mathematical induction. Let P of n be a property that is defined for integers n, and let a and b be fixed integers with a less than or equal to b. Suppose the following two statements are true. P of a plus 1, and so forth, and all the way up to P of b are all true. This is the basis step. For every integer k greater than or equal to b, if P of I is true for each integer I from a through k, then P of k plus 1 is true. That's the inductive step. Then the statement for every integer n greater than or equal to a, P of n is true. The supposition that P of I is true for each integer I from a through k is called the inductive hypothesis. Another way to state the inductive hypothesis is to say that P of a plus 1, and so forth to P of a, or P of k are all true. Now, applying this concept, the divisibility by a prime theorem states that any integer greater than 1 is divisible by a prime number. We prove this theorem using strong mathematical induction. So, theorem 444, any integer n greater than 1 is divisible by a prime number. The idea for the inductive step is this. If you are given an integer greater than 1, that is not itself a prime, then it is a product of two smaller positive integers, each of which is greater than 1. By inductive hypothesis, you are assuming that each of these smaller integers is divisible by a prime number, and so by transitivity of divisibility, those prime numbers also divide the integer you started with. So, the proof. Let the property P of n be the statement n is divisible by a prime number. Show that P2 is true. You must show that 2 is divisible by a prime number. But this is true because 2 is divisible by 2 and 2 is a prime number. Now show that for every integer k greater than 2, if P of I is true for each integer from 2 through k, then P of k is also true. P of k plus 1 is also true. So let k be an integer with k greater than or equal to 2. And suppose I is divisible by a prime number for each integer I from 2 through k. You must show that k plus 1 is divisible by a prime number. Case 1. I'm going to do two cases. If k plus 1 is prime, it is divisible by a prime number, namely itself. If k plus 1 is not prime, in this case, k of plus 1 equals a times b, where a and b are integers, with 1 less than k, less than a, which is less than k plus 1, and b also between 1 and k plus 1. Thus, in particular, 2 is less than or equal to A, which is less than or equal to K. So by inductive hypothesis, A is divisible by a prime number P. In addition, because K plus 1 equals AB, we have that K plus 1 is divisible by A. Hence, K is plus 1 is divisible by A, and A is divisible by P. By transitivity of divisibility, K plus 1 is divisible by the prime number P. So, therefore, regardless of whether K plus 1 is prime or not, it is divisible by a prime number. Since we have proved that both the basis and the inductive step of the strong mathematical induction, we conclude that the given statement is true. Define the sequence as follows. S sub 0 is 0, S sub 1 is 4, and S sub k is 6a sub k minus 1 minus 5a k sub k minus 2 for every integer k greater than or equal to 2. Find the first 4 terms of the sequence. It is claimed that for each integer n greater than or equal to 0, the nth term of the sequence has the same value as that given by the formula 5 to the n minus 1. In other words, the claim is that all terms of the sequence satisfy the equation S of n equals 5 to the n minus 1. Prove that this is true. So the first term, S sub 0, is 5 to the 0 minus 1, which is 1 minus 1. So it's 0. N equal to 1, 5n would be 5 to the first power, or 5. Minus 1 is 4. So that satisfies the second term. And so forth. So the second term is 24. Third term is 124. Now, to use strong mathematical induction to show that every term of the sequence satisfies the equation, the basis step must show that the first 2 terms satisfy it, which we already have done. This is necessary because, according to the definition of the sequence, computing values of later terms requires knowing the values of the 2 previous terms. So if the basis step only shows that the first term satisfies the equation, it would not be possible to use the inductive step to deduce that the second term satisfies the equation as well. In the inductive step, you suppose that for an arbitrarily chosen integer k greater than or equal to 1, all the terms of the sequence from S0 through S sub k satisfy the given equation, and you deduce that S of k sub k plus 1 must also satisfy the equation. So, let S sub 1, sub 2, sub 0, S sub 1, S sub 2, etc. be the sequence defined by specifying that S sub 0 is 0, S sub 1 is 4, and S sub k equals 6 times A sub k minus 1 minus 5 sub k minus 2. For every integer k greater than or equal to 2. And let the property P of n be the formula S sub n equals 5 to the n minus 1. Going to use strong mathematical induction to prove that for every integer n greater than or equal to 0, P of n is true. First, show that P of 0 and P of 1 are true. We already did that a couple of slides back. So S sub 0 is equal to 0, and S sub 1 equals to 1 or 4, which is what was the definition of S sub 0 and S sub 1 in the beginning. So the values agree with the values given in by the formula. Now that for every integer k greater than or equal to 1, if P of I is true for each integer I from 0 through k, then P of k plus 1 is also true. Let k be in any integer with k greater than or equal to 1, and suppose that S sub I is equal to 5 to the I minus 1 for every integer I from 0 to k. We must show that S sub k plus 1 equals 5 to the k plus 1 minus 1. Since k is greater than or equal to 1, we have that k plus 1 is greater than or equal to 2. So S sub k plus 1 equals this equation here. And then by definition of the hypothesis, you enter in, you substitute for S sub k 5 to the k minus 1, 5 to the k minus 1, and then multiply everything out, is 6 minus 1 times 5 to the k minus 1 by the law of exponents and factoring out the 6 and arithmetic, gets 5 to the k plus 1 minus 1, which, as was to be shown. So we have proved that both the basis and the inductive step of the strong mathematical induction, we conclude that the given statement is true. Now another sequence. A sub 1, A sub 2, A sub 3 is defined as follows. A sub 1 equals 0, A sub 2 equals 2, and A sub k equals 3a, the floor of k over 2 plus 2. I'm not going to find the first 7 terms of the sequence. I'll leave that for you guys to do on your own. But prove that a sub n is even for every integer n greater than or equal to 1. So the first 7 elements of the sequence are 0, 2 by the definition, and then 3 times a sub 1, 3 divided by 2 with the floor, plus 2 equals 3 times 0 plus 2, which is 2. And then 3 of a sub 2, 3 times a sub 2, which is 4 minus divided by 2, plus 2 equals 6 plus 2 is 8. 5 is the same because it uses the same numbers. 6 is, that's a typo. 3, oh yeah, no it's not. 3 of a sub 3, which is 2, equals 3 times a sub 3 plus 2 equals 8 again. And using the same numbers, you get 8 again for the 7th term. Let the property P of n be the statement the sentence A sub n is even. We use strong mathematical induction to show that the property holds true for every integer n greater than or equal to 1. Show that P of 1 and P of 2 are true. The property is true for n equals 1 and n equals 2 because a sub 1 is equal to 0 and a sub 2 is 0, and both 0 and 2 are even integers. So, show that for every integer k greater than or equal to 1, if P of I is true for each integer from I to 1, from 1 through k, then P sub of k plus 1 is also true. Let k be any integer with k greater than or equal to 1, and suppose that a sub I is even for each integer I with 1 less I being between 1 and k. By definition of a 1, 2, 3, a sub 1, 2, and 3, a sub k is equal to 3a sub the floor of k divided by 2 plus 2 for every integer k greater than or equal to 3. Now a sub floor of k divided by 2 is even by the inductive hypothesis, because k is greater than or equal to 1, and also 1 is less than or equal to k divided by 2 floored less than or equal to k. Thus 3a sub k divided by 2 is also even because it's a product of an odd and an even integer. Hence 3 sub floor of k divided by 2 plus 2 is even because the sum of two even integers is even. Consequently, a sub k, which equals to this quantity here, is even, as was to be shown. Since we have proved the basis step and the inductive step of the strong mathematical induction, we conclude that the given statement is true. Convention. Let us agree to say that a single number x1 is a product of one factor and can be computed with 0 multiplications. What does that mean? Say that a single number x1 is a product with one factor and can be computed with 0 multiplications. Okay. Prove that for any integer n greater than or equal to 1, if x sub 1, x sub 2, all the way up to x sub n are n numbers, then no matter how many parentheses are inserted into their product, the number of multiplications used to compute the product is n minus 1. The truth of the basis step follows immediately from the convention about a product with one factor. The inductive step is based on the fact that when several numbers are multiplied together, each step of the process involves multiplying two individual quantities. For instance, the final step for computing x sub 1 times x sub 2 quantity times x sub 3 times the quantity x sub 4 times x sub 5 is to multiply these two expressions. In general, when k plus 1 numbers are multiplied, two quantities in the final step each consists of fewer than k plus 1 factors. This is what makes it possible to use the inductive hypothesis. Proof. let the property P of n be the sentence if K sub 1, X sub 1, X sub 2, and on up to X sub n are n numbers, then no matter how many parentheses are inserted into their product, the number of multiplications used to compute the product is n minus 1. That's the property. Now, establish that P of 1, we must show that the number of multiplications to need to compute the product of X sub 1 is 1 minus 1. This is true because, by convention, X sub 1 is a product that can be computed with 0 multiplications. And 0 is equal to 1 minus 1. Now, show that for every integer k greater than or equal to 1, if P of I is true for each integer from 1 through k, then P of k plus 1 is also true. Let k be any integer with k greater than or equal to 1, and suppose that for each integer I from 1 through k, if x sub 1, x sub 2, all the way up to x sub I are numbers, then no matter how many parentheses are inserted into their product, the number of multiplications used to compute the product is I minus 1. We must show that x sub 1, x sub 2, all the way up to x sub k plus 1 are k plus 1 numbers. And no matter how many parentheses are inserted into their product, the number of multiplications used to compute the product is k plus 1 minus 1, or just k. Consider a product of k plus 1 factors. When parentheses are inserted in order to compute the product, some multiplication is the final one, and each of the two factors making up the final multiplication is a product of fewer than k plus 1 factors. Let L be the product of the left-hand factors, and R be the product of the right-hand factors, and suppose that L is composed of I factors and R is composed of R factors. Oh, I'm sorry, I guess that's a lowercase l. So then L plus R equals k plus 1, the total number of factors in the product. And L is between 1 and k, and R is between 1 and k. By the inductive hypothesis, evaluating L takes L minus 1 multiplications, and evaluating R takes R minus 1 multiplications. Because one final multiplication is needed to evaluate L plus times R, the number of multiplications needed to evaluate the product of all k plus 1 factors is L minus 1 plus R minus 1 plus 1, or L plus R minus 1, which equals k plus 1 minus 1, which equals k, as was to be shown. So, since we have proved the basis step and the inductive step of the strong mathematical induction, we conclude that the given statement is true. Theorem 541, existence and uniqueness of binary integer representations. Given any positive integer n has a unique representation in the form of n equals c to, sub r times 2 to the r, plus c sub r minus 1 times 2 to the r minus 1, plus so on and so forth to c sub 2 times 2 to the second, plus c sub 1 times 2 plus c sub 0, where r is a non-negative integer, c sub r equals 1, and c sub j equals 1 or 0 for each j, 0, 1, 2, 3, 4 up to r minus 1. The well-ordering principle for the integers. The well-ordering principle for the integers looks very different from both the ordinary and the strong principles of mathematical induction, but it can be shown that all three principles are equivalent. In other words, if any one of the three is true, then so are both of the others. The well-ordering principle for the integers. Let S be a set of integers containing one or more integers, all of which are greater than some fixed integer. Then S has at least one element. Has a least element, sorry. In each case, if the set has a least element, state what it is. If not, explain why the well-ordering principle is not violated. The set of all positive real numbers. Set of all non-negative integers n such that n squared is less than n. The set of all non-negative integers in the form 46 minus 7k, where k is an integer. Let's look at these individually here. A, there is no least positive real number, for if x is any positive real number, then x divided by 2 is a positive real number that is less than x. No violation of the well-ordering principle occurs because the well-ordering principle refers only to sets of integers, and this set is not a set of integers. There is, for B, there is no least non-negative integer n such that n squared is less than n, because there is no non-negative integer that satisfies this inequality. The well-ordering principle is not violated because the well-ordering principle refers only to sets that contain at least one element. The following shows, this table here shows the values of 46 minus 7k for various values of k. The table suggests, and you can easily confirm, that 46 minus 7k is less than 0 for k greater than or equal to 7. And that 46 minus 7k is greater than or equal to 46 for k less than or equal to 0. Therefore, from the other values in the table, it is clear that 4 is the least non-negative integer of the form 46 minus 7k. This corresponds to k equals 6, right here. So, quotient remainder theorem, existence part. Given any integer n and any positive integer d, there exists integers q and r such that n equals dq plus r, and that r is greater than or equal to 0 and less than d. So, restating what we covered in a previous lecture about the quotient remainder theorem. And that's it for that one. And we'll move on to section 5. All right. Correctness of algorithms. What does it mean for a computer program to be correct? Each program is designed to do a specific task. Calculate the mean or median of a set of numbers, compute the size of the paychecks for a company payroll, rearrange names in alphabetical order, or whatever. We will say that a program is correct if it produces the output specified in its accompanying documentation for any set of input data of the type specified in the documentation. Assertions. Consider an algorithm that is designed to produce a certain final state from a certain initial state. Both the initial and final states can be expressed as predicates involving the input and output variables. Often the predicate describing the initial state is called the precondition for the algorithm, and the predicate describing the final state is called the postcondition for the algorithm. Here are pre- and post-conditions for some typical algorithms. Algorithm to compute a product of non-negative integers. Precondition, the input variables m and n are non-negative integers. Postcondition, the output variable p equals mn. Algorithm to find the quotient and remainder of the division of one positive integer by another. Precondition, the input variables a and b are positive integers. Postcondition, the output variables q and r are integers such that a equals bq plus r, and that r is greater than or equal to 0, but less than b. Algorithm to sort a one-dimensional array of real numbers. Precondition, the input variable a sub 1, a sub 2, etc. up to a sub n is a one-dimensional array of real numbers. The output variable is the postcondition is the output variable b of b sub 1, b sub 2, all the way up to b sub n is a one-dimensional array of real numbers with the same elements as a, but with the property that b sub I is less than or equal to b sub j whenever I is less than or equal to j. Loop invariance. The method of loop invariance is used to prove correctness of a loop with respect to certain pre- and post-conditions. It is based on the principle of mathematical induction. Suppose that an algorithm contains a while loop and that that entry into this loop is restricted by a condition G called the guard. Suppose also that assertions describing the current states of the algorithm variables have been placed immediately preceding and immediately the loop. Immediately preceding and immediately the loop. The assertion just preceded the loop is called the precondition for the loop, and the one just following is called the postcondition for the loop. The annotated loop has the following appearance. Precondition for the loop, the while keyword, statements in the body of the loop, none contain branching statements that lead outside the loop, and the while loop, and then you have the postcondition for the loop. A loop is defined as correct with respect to its pre- and post conditions, if and only if, whenever the algorithm variables satisfy the precondition for the loop and the loop terminates after a finite number of steps, the algorithm variables satisfy the postcondition for the loop. A loop invariant is a predicate with domain a set of integers, which satisfies the following condition. For each iteration of the loop, if the predicate is true before the iteration, then it is true after the iteration. Furthermore, if the predicate satisfies the following two additional conditions, the loop will be correct with respect to its post-conditions, pre- and post-conditions. The predicate is true before the first iteration of the loop. If the loop terminates after a finite number of iterations, the truth of the loop invariant ensures the truth of the post-condition of the loop. The following theorem called the loop invariant theorem, formalizes these ideas. It was first developed by this fellow or lady in 1969. Let a while loop with guard G be given, together with pre and post conditions that are predicates in the algorithm variables. Also let a predicate I sub n, called the loop invariant, be given. If the following four properties are true, then the loop is correct with respect to its pre and post condition. Basis property. The precondition for the loop implies that I sub 0 is true before the first iteration of the loop. Inductive property. For every integer k greater than or equal to 0, if the guard G and the loop invariant I sub k are both true for the iteration of the loop, then I sub k plus 1 is true after an iteration of the loop. Eventual falsity of the guard. After a finite number of iterations of the loop, the guard G becomes false. Correctness of the post condition. If n is the least number of iterations after which G is false and I sub n is true, then the values of the algorithm variables will be as specified in the post condition of the loop. The loop is designed to compute the product of mx for a non-negative integer at m and a real number x, without using built-in multiplication operation. Prior to the loop, variables I and product have been introduced and given initial values I equals 0 and product equals 0. Precondition. M is a non-negative integer. X is a real number. I equals 0 and product equals 0. While and the loop is while I does not equal to M, product equals product plus X, and then I equals I plus 1. Post condition, the product equals mx. Let the loop invariant be I sub n equals is I equal to n, and the product equals n times x. The guard condition of the loop is I does not equal to m. Use the loop invariant theorem to prove that the while loop is correct with respect to the given pre and post conditions. Well, the basis property, I sub 0, or I of 0, is true for the first iteration of the loop. I of 0 is I equals 0 and product equals 0 times x, which is true for before the first iteration of the loop, because 0 times x is 0. Inductive property. If G is true and I of k is true before a loop iteration, where k is greater than or equal to 0, then I of k plus 1 is true after the loop iteration. Suppose k is a non-negative integer, such that G and I of k is true before an iteration of the loop. Then as execution reaches the top of the loop, I does not equal m, product equals k sub k times x, and I equals k. Since I does not equal m, the guard is passed and the statement 1 is executed. Before execution of statement 1, old product equals k of x, k times x. Thus, execution of statement 1 has the following effect. New product equals old product plus x, which is k times x plus x, which equals k plus 1 plus x, or times x. Similar, before statement 2 is executed, the old I is equal to K. So after a statement, execution of statement 2, I equals I equals I plus 1, which equals to K plus 1. Hence, after the loop iteration, the statement I of K plus 1, namely I equals K plus 1 and product equals K plus 1 times X, is true. This is what we needed to show. Eventual falsity of the guard. After a finite number of iterations of the loop, G becomes false. The guard is the condition I does not equal to M, and M is a non-negative integer. By 1 and 2, it is known that for every integer n greater than or equal to 0, if the loop is iterated n times, then I will equal to n, and the product will equal n times x. So after m iterations of the loop, I equals m. Thus, G becomes false after m iterations of the loop. Correctness of the post condition. According to the post condition, the value of the product after execution of the loop should be m times x. But if G becomes false after n iterations, I equals m. And if I of n is true, I equals n, and the product equals n times x. Since both conditions, G false and I of n true, are satisfied, then m equals I, which equals n, and the product m times x is as required. Correctness of the division algorithm. The division algorithm is supposed to take a non-negative integer a and a positive integer d and compute the non-negative integers q and r such that a equals dq plus r, and and r is greater than or equal to 0 but less than d. Initially, the variables r and q are introduced and given the values r equals a and q equals 0. The crucial loop, annotated with pre and post conditions, is as follows. Precondition, a is a non-negative integer, and d is a positive integer. R equals a, and q equals 0. The loop is while d is greater than or equal to d, r equals r minus d, and q equals q plus 1. Post condition. Q and R are non-negative integers with the property that a equals qd plus r, and r is greater than or equal to 0 and less than d. Correctness of the Euclidean theorem. The Euclidean theorem is supposed to take integers a and b with a greater than b and b greater than or equal to 0 and compute their greatest common divisor. Just before the crucial loop, variables a, b, and r have been introduced with lowercase a equals a, lowercase b equals b, and lowercase r equals b as well. The crucial loop, annotated with pre and post conditions, is the following. With a greater than b greater than or equal to 0, a equals a, b equals b, and r equals b, r equals a mod b, little b. A, little a then equals to lowercase b, and then lowercase b equals r. And the post condition is a equals the greatest common divisor of large A and b. So that's how you would program the Euclidean theorem in a program. But That'll be about it for the day, I think. Kind of a brief day today. I guess I will see you on Tuesday.